What if a critical step is missing in most of thermodynamic textbooks? The characterization of the absolute zero through limiting Carnot engines. My name is José María Martín-Olalla. I'm professor at the University of Seville in Spain, and in this video I'm going to explain, to clarify the proof of the Nernst theorem that was presented in June 2025. This video is a reply to a comment published in March 2026 by Chen et al., professor at the Chinese university, which commented my early proof on the Nernst theorem. This proof was based on the fact that the temperature must be characterized by Carnot engines and by the Carnot theorem. Chen et al. Challenged that the Carnot theorem does not operate at t equals 0, but this is to say that t equals 0 cannot be characterized from a thermodynamic point of view. And this is quite strange, because usually physical quantities, and the temperature is a physical quantity, have characterized zero value. For instance, when we speak about a length equal to 0, we are just saying that the two things are kept in touch, for instance. When we speak of null mass, we are speaking about the system we have removed any particle or any matter whatsoever. So the problem, of course, with temperature is that we lack a visualization of a body without temperature, but from a fundamental point of view, t equals 0 should be assessed, should be characterized in a consistent universal way, and this is the object of this video. I am going first to explain the setting of the problem, mainly the second law of thermodynamics. Then I will be explaining how this problem has been accessed or dealt with by previous researchers, and then I will put forward my point of view on how we can assess temperature equal to 0 from a universal and consistent point of view. So in the 18th century, people were trying to understand the properties of the hydrostatic system, gases, liquids, and solids. So here we have a setting in which we have here, this is our system under test, and our thermodynamic system, which is at atmospheric pressure. This pressure will not be changing in the experiment, and it is immersed in a thermal bath, which is just water flowing in and coming out here. So we can change the temperature of the water, and by changing the temperature of the water, see that the thermometer is changing the value. We are collecting volume, and usually the system just will expand. And so we can collect volume versus temperature here in this chart on the right, and we will be seeing a fairly linear relationship between volume and temperature in this setting. So this linear relationship can be expressed as P0 plus AT. If T is the normal, the usual Celsius scale, this will be T equals 0, the point of freezing water, and this A would be a linear coupling. So for most of the gases, for most of the gases, provided that the density is low enough, we will have observing that by every 100 change in the temperature, we would have something like a 36.61% change in the volume. And people just were saying, okay, if I get the sample cooled, I decrease the temperature, then the volume will be decreasing, and there will be a point where the volume will be 0, and this extrapolation would give me a very strange point where apparently the system won't be able to be cooled any further. So this was the first idea of absolute zero, and it happened that this value, this extrapolation, worked remarkably well. and it was the same value for different chemical species, let's say oxygen, nitrogen, argon, and so on. So this was the idea of absolute zero, and this number, I mean the reciprocal of this coefficient, which is the expansion coefficient of the ideal gases, was quite accurate. I mean, it was 273.15 kelvins. Okay, here I have set this as a degree Kelvin because this is a scale. This is still a scale of temperature in the sense that this is a property which is given or which is observed for hydrostatic substances, mainly for gases. It is not a universal thing. I mean, magnetic substance or paraelectric substance may have a different absolute zero. Of course, we know that there is just one universal absolute zero, but this is not. It is not this kind of experiment that is showing us that this is a universal thing. The point going forward and going to a universal characterization of the absolute zero needs of the works developed by none other than Carnot. Carnot studied the heat engines at the beginning of the 19th century and noted that for the engine to work, I mean for providing some useful work that rises a wave, we need a boiler and we need a refrigerator, and it is something that is coming from the boiler towards the refrigerator that causes this wave to rise. I mean, provides the work. And Carnot was wrong he was attributing this thing to the heat. It is not heat that is coming from the boiler to the refrigerator in order to provide work, or it is not in the sense that Carnot thought, but was able to underpin some critical ideas. First, that ideal reversible engines would perform the best. I mean, any work would be the greatest if this engine ideally operates reversibly, meaning that the operating engine here works without friction, without any kind of gradients, and as long as this is ideal, the work will be the greatest for a given amount of this quantity, meaning that this work is determined by nature, by a law that we are going to set forward here, meaning also that this work was universal, was independent on the characteristic of the substance that was undergoing the cycle. And this is critical to understand the universal character of temperature. William Thomson, that later became Lord Kelvin, noted that the Carnot engine provided a universal thermometer, and he noted that if the boiler and refrigerator differs in 1 degree, then the work would be the same no matter which is the setting temperature. I mean, it doesn't matter if this temperature is 100 degrees or 200 degrees or 0 degrees. If the temperature difference is 1 degree, I mean, this quantity will be always the same, regardless of the substance that is undergoing the cycle. Thomson was setting the idea that the Carnot engine is a universal thermometer. But curiously, Thomson was not thinking about the zero of the scale, about the absolute zero. He was just thinking, or was just regarding with the problem of the unit of temperature. And Thomson was also attributing this quantity to the idea of heat. This is incorrect, but I mean, this equation stands as long as this quantity is properly identified. And the person who identified this property was none other than Rudolf Clausius. Rudolf Clausius noted that the Carnot engine has 2 points of view. The point of view, the energetic point of view, in which, yes, we extract heat from the boiler, but this heat is shared in the form of work and in the form of heat supplied to the refrigerator or the cooler. And Clausius noted that, on the other hand, there is a thing that he called initially equivalent of heat, and later he called entropy, that comes from the boiler to the refrigerator exact. I mean, this is a true conservation law if the engine is reversible. And that fitted to the previous idea by Carnot. I mean, it is this thing that is coming from the boiler to the refrigerator and causing the work and the raising of the wave. This entropy was just the relation between heat and temperature. So this is kind of saying, okay, it does matter how much heat do you exchange with the boiler, but it also matters how much how much temperature has the boiler. So on the other hand, he was able to write this equation, which is now the expression of the Carnot theorem. It is also somehow the Clausius theorem, which provides a kind of a definition or kind of an idea of how we can measure temperatures with Carnot engines. But the important thing here is that both Thomson and Clausius noted that this is possible, but this thing is impossible. I mean, it is impossible to run these engines not in reverse way, but in the opposite way, meaning that we need two things. We need a boiler and we need a refrigerator, but it is not a question of having two items here to make the engine run. The boiler can only play the role of a boiler, and the refrigerator can only play the role of a refrigerator. I mean, the roles cannot be exchanged. And this thing was more perfectly stated by none other than Max Planck, who noted that in the end it is impossible to cool a body and rise a wave. So this engine is impossible, or this kind of engine is impossible. And this is the most perfect formalization of the second law of the thermodynamics. And the thing to note here is that because we have reduced the problem to just one body, we are not speaking here of a boiler, or we are not speaking here of a refrigerator, we are just speaking of a body. This means that this statement, this idea that this is impossible, is independent of temperatures. Temperature is completely alien to this postulate, to this statement. Therefore, temperature arises as a consequence of this postulate. And this equation that we saw earlier, this is not only a thermometer, but it is a true definition of temperature from a thermodynamic point of view. But the thing is that Planck's statement of the second law prevents the existence of engine with this Q to the refrigerator equal to 0. So if this QC can't be 0, the thing is, how can T equals 0 be assessed? And this is the problem, the tricky problem that we are now facing. So this problem was first discussed by Walter Nernst and Albert Einstein. So here we have the Carnot engine. This is the entropy exchange of the engine, and we have here a chart with entropy and temperature. So the Carnot engine here is just a rectangle. Here this is an isothermal process where the boiler exchanges entropy with the engine, and now we have here another isothermal process where the refrigerator exchanges the opposite entropy with the engine. So this area is the work, the total work, and this area, which is not shaded, this area, is the heat exchanged with the refrigerator. So it is perfectly fine, this setting, in order to measure the temperature of the refrigerator or the temperature of the cooler. And it is perfectly possible to change the conditions so that the difference between the boiler and the refrigerator or cooler is becoming larger and larger, and the heat exchanged with the refrigerator is becoming smaller and smaller. But as long as this operates in this way, I mean, this is perfectly fine. Okay? So the only problem here, and let's have a look to this. I mean, here I have here in gray values of a mechanical variable. This mechanical variable can be the volume, the pressure, magnetic field, magnetization, whatever mechanical variable you may wish. So let's have a look at this cycle, and specifically to this process. Now here, the system undergoing the cycle, if it is an hydrostatic substance, it will be making kind of a compression, something like this. So we will be doing this kind of process. Okay? So the thing is that when we are getting the refrigerator, the cooler, closer and closer to the zero, this is perfectly fine. The heat is shrinking to zero, not the entropy, but the heat. And at the very moment that this isotherm becomes zero, this engine is impossible. Nernst said that this is impossible because the engine would negate the second law, the statement posted by Planck. And Einstein said that the thing to note is that when you try to make this compression at the absolute zero, every imperfection, any imperfection, no matter how slight, any friction, anything, would drive the temperature of the system away from T equals zero, and therefore this engine couldn't be run. So either way, T equals zero is not characterized, and this is a paradox for a fundamental physical magnitude. Well, the thing to note is that experimentally, this array of entropy values at the absolute zero is not observed. We always observe how this line collapses into one single point at the absolute zero, and then we have something like this. So all the lines of x, iso x lines, comes to a point in t equals zero, and therefore there arises a region like this one where there is no accessible state. I mean, it is impossible to find a state for this system because there is no value of the mechanical variable for its domain to fit this entropy and this temperature. So it means that we have here we had an empty space. We have no restriction. But now we have a restriction. We need to fit to this white area where the mechanical variable can set the temperature and entropy that we are dealing with. So we can make a Carnot engine here like this one. There is no problem with doing that. But if we wanted to go down to zero, we need to perform a series of distortion. We need to decrease the temperature range between the cooler and the boiler, and we need to decrease the entropy exchange in the Carnot engine. And it is the only way by which we can set this Carnot engine very close to zero. So note that this is a regular Carnot engine, a four-stroke Carnot engine, but we are shrinking both the entropy and the temperature between the cooler and the boiler, between the refrigerator and the boiler. In the end, at t equals zero, we come to a single point. So the four-stroke engine degenerates into one point. It is a null engine with finitless change of entropy and finitless change of temperature. Liboff said in 1994 that at T equals 0, a Carnot engine does not exist and the Kelvin temperature scale is not defined. And again, this is a paradox because the temperature is not a scale, the temperature is a fundamental physical magnitude whose unit is defined in the international system of units. Therefore, we need to set a proper way of understanding what is T equals 0 from a fundamental point of view. Now, for a solution to this problem, let's consider the following idea. So here we have the Carnot engine, we have the change of entropy at the boiler and at the cooler or refrigerator, and we have here the layout, the schematic of this Carnot engine. And we can distort, restyle this Carnot engine in the following way. So if we move this way, we are not changing the global, the overall picture of the thing. We are changing the way in which we run the cycle. We are changing the engineering behind the cycle, but we are not changing the physics behind the cycle, the physics and the mathematics. So it is exactly the same. It doesn't matter. I mean, for instance, the area, the work is exactly the same for this parallelogram and for this rectangle. No change. We don't need this to be a straight line. We could even distort this straight line and make something like this, and it would work perfectly fine. As long as this and this are parallel to each other, there is no problem. This is still a Carnot engine. Okay? And therefore the thing is that we have limitation in our accessible space. We have a restriction. This is a cone, but we are no longer restricted to make this kind of rectangles. We can do something like that. And the point to note is that here we have the change in the boiler, and we set x1 and x2. This is, freely set by the experimentalist. But then we find a temperature T star so that this delta S matches with the range of entropy at this temperature. Here we are changing the mechanical variable, for instance, for 0 to infinity. We are exhausting the domain of the mechanical variable. When we exhaust the domain of the mechanical variable, we fit a change of entropy. If this change of entropy equals to the change of entropy in the boiler, it means that we find the limiting temperature for this Carnot engine. For this working system, it is impossible to perform a Carnot engine with this change of entropy at any temperature lower than this T star. So the thing now is change x2. We decrease x2, and by decreasing x2 or increasing x2, it depends on the substance, we would be decreasing delta S, and by decreasing delta S we will be moving T star down to 0. And here we have a 4-stroke engine, a 4-stroke engine, and 4-stroke engine. We are decreasing delta S, but we are increasing delta T. We are not moving the temperature of the boiler. This is a 4-stroke Carnot engine, this is a 4-stroke engine, 4-stroke engine, and in the limit T to 0, we are only shrinking delta S. We are not shrinking delta T. We are always setting a comparison between a boiler at T equal 1 and a refrigerator, a cooler, at a temperature which is close to 0. At the very end, we get a 2-stroke engine. The 4-stroke engine degenerates into a touch and go, a 2-stroke null engine, where the entropy comes to 0, but the delta T, the amplitude and temperature, is not 0. So then the argument by Einstein does no longer apply, because you don't need to make any kind of process at T equals 0. You just touch T equals 0 and then go. Of course, this is conceptual. I mean, we are not thinking of doing this kind of experiment by any means. So that's the way in which the absolute zero is consistently characterized by Carnot engines and by the Carnot theorem. I have made another presentation here in which I compare the Einstein argument, the Liboff argument, and my argument. Here also showing a caliper on the jaws of a caliper, which kind of speaks about the measurement we are doing about delta t. So we run the simulation, and there is no problem with the Einstein point of view and with my point of view. I mean, it's pretty fine. The structure, the idea by Liboff, the problem is that the temperatures are getting closer and closer, and it's kind of, if the caliper is just getting thinner and thinner and just in practice disappearing. So I am not going to discuss any further this option, this choice, but the thing for these two settings, the point with these two settings, it is like if at t equals 0, the caliper in the Einstein's version just disappears, whereas in the setting I am proposing, yes, this caliper, it just happened that the jaws come to each other in contact, and therefore we are having a null measurement, and this null measurement is perfectly consistent with the formulation of the second law. So that's all. The idea then is that Nernst's theorem is just the application of Carnot's theorem at t equals 0, and that Carnot's theorem can consistently operate in the very limit t equals 0. The domain of the temperature that follows from Planck's statement of the second law is therefore t greater equal than 0, and Nernst's experimental observations are just evidence that the above ideas are valid, specifically that the idea that the statement of the second law consistently defines the temperature as a physical observable from t equals 0 to any temperature non-zero. You can find this slide in Zenodo under this DOI. Here you have the references. Many thanks for your attention and have a nice day.